For most of human history, the origin of the world was explained through myths, legends, and oral traditions. Sumerians, Egyptians, Greeks, and indigenous peoples of the Americas each created their own narratives to answer the same essential question: how did everything begin? These stories helped entire civilizations understand their place in the world long before science existed. Only in the last few centuries did humanity begin to investigate this question systematically, using observation, mathematics, experimentation, and physical records left by the universe itself. The story we know today was not extracted from sacred texts, but from the light emitted by distant galaxies, from the radiation left behind by the Big Bang, and from chemical signatures preserved in the oldest rocks on Earth. This documentary presents the most solid narrative ever constructed about the origin of the world, based on current scientific consensus. A story written from observable data, precise measurements, and evidence accumulated over decades, from the birth of the universe to the emergence of the first living beings. This is the real history of how everything began, the birth of the universe. About 13.8 billion years ago, there were no stars, planets, or galaxies. Space and time as we understand them did not yet exist. All the matter and energy of the universe were concentrated in an extremely hot and dense state. This initial moment is known as the Big Bang. The Big Bang was not an explosion occurring at a point in space. It was the expansion of space itself. As the universe expanded, its temperature decreased, allowing energy to transform into elementary particles. In the first minutes, these particles combined, forming the first nuclei of hydrogen and helium. After approximately 380,000 years, the universe cooled enough for atoms to become stable and for light to travel freely. That light can still be detected today as the cosmic microwave background radiation, one of the main observational pillars of modern cosmology. Even so, for hundreds of millions of years, the universe remained without stars, immersed in darkness, a period known as the Cosmic Dark Ages. The first stars, galaxies, and elements. Over time, small density variations in primordial clouds of gas began to intensify under the influence of gravity. Denser regions attracted more matter, collapsing and giving rise to the first stars, known as population 3 stars. These stars were enormous, far more massive than the Sun, and lived for relatively short periods. In their cores, nuclear reactions produced for the first time elements heavier than hydrogen and helium, such as carbon, oxygen, silicon, and iron. When these stars exploded as supernova, they scattered these elements throughout space. From this enriched material, the first galaxies began to form. Some can still be observed today, such as GNZ11, seen as it was when the universe was only about 400 million years old. Others, including Andromeda, the Milky Way, and the Triangulum Galaxy, formed later, becoming stable structures where new generations of stars would continue to be born. The formation of the solar system, about 4.6 billion years ago, in one of the spiral arms of the Milky Way, an interstellar cloud rich in gas and dust began to collapse. At its center, the Sun formed. Around it, the remaining material organized into a protoplanetary disk, giving rise to planets, moons, asteroids, and comets. Earth emerged from this process as a young, hot, and unstable planet. Its surface was covered by oceans of magma and constantly bombarded by meteorites. One of these impacts likely led to the formation of the Moon. The early atmosphere was dense and toxic by today's standards, composed of methane, ammonia, carbon dioxide, and water vapor. With no free oxygen, over hundreds of millions of years, the planet gradually cooled. Water condensed, forming the first liquid oceans. These oceans not only shaped Earth's surface, but also created the ideal environment for complex chemical reactions. The next major step in this story, the chemistry that preceded life. In the oceans of early Earth, simple molecules interacted continuously. Energy sources such as lightning, volcanism, geothermal heat, and solar radiation drove increasingly complex chemical reactions. In the 1950s, an experiment conducted by Stanley Miller and Harold Urey demonstrated that amino acids, the fundamental components of proteins, can form spontaneously from simple compounds under conditions similar to those of early Earth. This result strengthened the idea that life could arise through natural processes. Over millions of years, some of these molecules formed more organized structures capable of storing chemical information and replicating imperfectly. This gradual process is known as chemical evolution and represents the transition from a purely chemical planet to a biologically active, 1. The first living beings. The oldest geological and isotopic evidence indicates that life emerged on Earth about 3.8 billion years ago. The first living beings were extremely simple, single-celled organisms similar to modern bacteria and archaea. These organisms did not use oxygen and obtained energy through simple chemical reactions. For billions of years, life remained microscopic but not inactive. Slowly, these organisms altered the chemical composition of the oceans and the atmosphere. Some developed the ability to perform photosynthesis, releasing oxygen as a byproduct. The gradual accumulation of this gas led to the event known as the Great Oxidation, around 2.4 billion years ago. This transformation radically changed the planet, allowing more complex forms of life to emerge in the future. The cell that changed everything. For nearly 2 billion years, life on Earth remained restricted to simple, single-celled organisms. Even so, these microorganisms had already profoundly transformed the planet, particularly its atmosphere. The gradual buildup of oxygen enabled more efficient ways of obtaining energy, creating unprecedented conditions for biological evolution. Around 2 billion years ago, a decisive milestone appeared: eukaryotic cells. Unlike bacteria, these cells possessed a defined nucleus and specialized internal compartments. The most widely accepted explanation for this innovation is the endosymbiotic theory, which proposes that one cell came to house another, giving rise to structures such as mitochondria. This change represented a fundamental evolutionary leap. For the first time, life had access to large amounts of energy in a controlled way. This made it possible to sustain larger, more complex cells with specialized functions. The foundation of complex life was established, preparing the ground for something even more extraordinary: organisms made of many cells, working together when life took shape. With more efficient cells, evolution began to experiment with new forms of organization. The first multicellular organisms appeared, initially simple, composed of groups of cells with distinct functions. The oldest evidence of these beings appears in the fossil record of the Ediacaran period, about 600 million years ago, revealing soft-bodied organisms living in shallow oceans. That period marks the transition from a planet dominated by microorganisms to a world where life began to occupy physical space in visible form. For the first time, organisms displayed body symmetry, tissue differentiation, and more complex ecological interactions. Life was no longer only microscopic. This process reached its most dramatic point during the Cambrian explosion, approximately 541 million years ago. In a relatively short geological interval, most of the major animal groups known today emerged, including arthropods, mollusks, and the first chordate. Eyes, primitive nervous systems, skeletons, and active behaviors appeared. Life was no longer simply existing, it was rapidly diversifying, inaugurating a new era in Earth's history. Over billions of years, the universe moved from simplicity to complexity, governed by the same physical laws since the Big Bang. On Earth, life emerged, remained microscopic for ages, became multicellular, and gradually developed bodies, senses, and increasingly sophisticated ways of interacting with the environment. Nothing happened suddenly. Each stage prepared the way for the next in a continuous process of transformation. Much later, in an extremely recent moment of this long history, a singular chapter appeared. Homo sapiens emerged in Africa about 200,000 years ago, after an evolutionary process that unfolded over millions of years. Before modern humans, other hominins already walked the planet. According to the Human Origins program at the Smithsonian's National Museum of Natural History, scientists recognize between 15 and 20 different species of early humans. Some coexisted, others vanished, and many still raise questions about how they were related. How did this specific lineage arise? What happened to the other human forms? And why, among so many evolutionary possibilities, did our species remain? That is the next story.